Hi, I'm Dr. Christopher Sutton, and welcome back to my Introduction to GIS video series. In this video, we will continue our examination of key geographical concepts with scale. Scale influences how we view, analyze, and interpret spatial data. Geographers understand that phenomena can be represented at different scales and that these representations impact our understanding of these phenomena. In GIS, scale affects the resolution of data, the level of detail in spatial analyses, and the design of maps. We tend to find the term scale used in multiple contexts in GIS. First, we have analysis scale, which is the level of geographic detail at which phenomena are analyzed. There is temporal scale, which is the time frame used for an analysis. And then there's map scale, which is the ratio between distance on a map and the corresponding distance on Earth. Let's look at these in a little bit more detail. Scale is a critical concept in GIS because it determines the level of detail and accuracy in spatial data, directly influencing how data are collected, analyzed, and interpreted. Here are the key reasons why scale is important. First is detail and resolution. For example, examining a geographical feature like a forest using satellite imagery might show its size and location relative to other features. However, examining a ground-level survey of that forest could reveal details about the types of trees, the biodiversity, the undergrowth conditions, and other characteristics. Different phenomena occur at different spatial scales. For instance, the study of global climate patterns requires a different scale than analyzing local traffic patterns. Using an inappropriate scale can lead to misleading or inaccurate conclusions. The scale of analysis impacts how data are represented in GIS. For example, a map showing land cover patterns at a continental scale will represent data differently compared to a map focused on a single county. At a larger scale, more details are visible and the analysis can be more precise. Conversely, at a smaller scale, details are generalized and the focus is on broader patterns. Some phenomena are only observable or relevant at certain scales. For example, soil composition details might be crucial in a local agricultural study, but irrelevant in a continental study of broad climate zones. Temporal scale is the time frame used for analysis. In GIS, it is common to examine the spatial change of a phenomenon over time. GIS analysis can vary in temporal scale. One might examine phenomena using short time periods like hours or days. For example, studying traffic patterns in a city. Long-term analyses, like examining changes in land cover or climate, might span years, decades, or centuries. Map scale is the relationship between map distance and Earth distance. Map scale affects the amount of detail that can be portrayed. Here we have a portion of the Macomb, Illinois quadrangle from the U.S. Geological Survey. The scale of this map is 1 to 24,000. This scale depiction is called the representative fraction, or RF scale. RF scales display the map scale as the relationship between one unit of distance on the map and the corresponding Earth distance in those same units. If we place a ruler on the map, 1 unit of measured distance corresponds to 24,000 of the same units on Earth at this scale. When using this scale, keep in mind that the units are the same on either side of the ratio. For example, at 1 to 24,000, we are saying 1 inch on the map represents 24,000 inches on Earth. Or, if we were to use metric, 1 centimeter on the map represents 24,000 centimeters on Earth. There are several commonly used map scales, especially in USGS maps, including 1 to 62,500, 1 to 100,000, and 1 to 1 million. If we look at a 1 to 100,000 map scale, we're saying 1 inch on the map represents 100,000 inches on Earth, or 1 centimeter on the map represents 100,000 centimeters on Earth. We tend not to use inches or centimeters for measuring long distances on Earth. Instead, we use miles or kilometers. So what is a map scale relationship in terms of miles or kilometers? Let's look at the 1 to 100,000 map scale to get a better sense of this relationship. To begin with, we have to ask how many inches are in a mile and how many centimeters are in a kilometer. With inches in a mile, we know that there are 12 inches in a foot and that there are 5,280 feet in a mile. Multiplying those two reveals that there are 63,360 inches in a mile. Thus, an inch of map distance at a scale of 1 to 100,000 represents approximately 1.6 miles of distance on Earth. When examining the metric version of the 1 to 100,000 map scale, we need to calculate how many centimeters are in a kilometer. We know that there are 100 centimeters in a meter, and that there are 1,000 meters in a kilometer. Multiplying those two together reveals that there are 100,000 centimeters in a kilometer. So 1 centimeter on our map is representing 1 kilometer of real-world distance. In GIS software, the map scale is always visible to you. Here we have an example of an aerial photograph of Macomb, Illinois. The scale of this map is 1 to 24,000. In our software, we can change the map scale either by choosing from a list of predetermined map scales or typing in the map scale that we want. Let's change this map scale to 1 to 7,500. When we do this, the map zooms in and we are looking more closely at downtown Macomb, Illinois. Conversely, you can do the same by entering a different number where the map will zoom out and you will see a much larger space being represented. Understanding scale in GIS is important for making accurate and effective decisions. In the next video, we will continue our examination of geographical concepts that are deployed in GIS with direction.